Yes.
Can you hear me?
Yes, perfectly.
Yeah.
Great. And are you able to see the slides?
As well, yeah.
Okay, so if there are questions, maybe feel free to just, there are not that many people in this Zoom, so feel free to just unmute yourself or write in the chat. And I don't know if I'll try to monitor it. Okay, so thanks for the organizers for carrying this, organizing this conference through, despite the war and despite other challenges. Speaking of which, I'm not going to talk about the war, but just if there, I have a lot of experience. I lived and worked in Israel, in Canada, in the US. So if anyone wants to learn or has any questions, I'll leave my email in the chat. And I'm traveling now, but I'll try to respond. So today I'll talk about optimization-friendly generic mechanism design without money. Okay, so I'll introduce the general topic. It's so the general topic is mechanism design. So what is, at the high level, what is mechanism design? So traditional algorithm design, we have an input, we have an output, and the algorithm is supposed to get us from the input to the output. And there is a whole field, even when the output is just obtaining some objective, like in optimization, it's a huge field with positive and negative results and of algorithm design. So mechanism design adds an extra level here where the input, let's see if we can get a pointer. Yeah, where the input is not given to us in some hard form, but actually is reported by some agents who actually are interested in the output. So for example, in an auction, you get willingness to pay comes from the agents, but they also care about how much they pay. So they might underreport, for example, their utilities in order to pay less in the end. So when we have to take those issues into account, this is a mechanism. And kind of the general theme of this field of algorithmic mechanism design is this question of how much more difficult it is to do optimization on strategic inputs compared to known inputs. And the holy grail, kind of the dream, is to make this question go away. So essentially have some black box reduction or some reduction, generic reduction, that takes an algorithm where we have an algorithm, maybe we worked very hard, maybe it's underspecified, maybe it's a heuristic, like when you train a machine learning model, we don't fully understand how it works, but we have some algorithm that works on known inputs, and we want to turn it into a mechanism that works on strategic inputs, on reports of agents who are interested in the outcome and who will try to manipulate it. Okay, so what's a reduction in general? So very common theme in this field is actually a non-reduction, so solving the same problem but in a very different way. So for example, so that's of course always an option. A black box reduction is perhaps the strongest form of reduction, where the mechanism would make calls to the algorithm. So you're allowed to, you have someone gives you a black box with the algorithm, you're allowed to make calls to it, and based on that, you're supposed to compute the outcome of the mechanism. An open or white box reduction is one where you're allowed to modify the algorithm. And one hope for both black box and especially white box reductions is that they would work even if you're a heuristic and not an algorithm. So, and non-reductions, usually you have to rely on a specific solution concept. And typically it's lossy in the sense that if your algorithm is some machine learning heuristic that's at the edge of humanity's ability to solve the problem, it's hard to imagine that you can solve it from scratch in order to get a mechanism. So for that reason, it's nicer if we have a reduction that can work even on heuristics. So today we'll discuss one generic framework for taking an iterated optimization-based algorithm, which is now very common in several contexts: in machine learning, online optimization. So iterated, basically any kind of algorithm that's locally is an iterated optimization, and turning it into a mechanism without money. So we'll define. We'll see examples of this. So the departure point for this work is a three-way connection between optimization, convex optimization, but also other forms of optimization, online learning, and concepts from game theory of correlated equilibria. And every pair of those has been explored extensively. We'll kind of make use of all three simultaneously, but every pair, there are textbooks that talk about, say, online optimization in the context of learning, or so those are not new connections, but we'll try to put them together in a new way to obtain a new generic reduction. So the ingredients we'll need is perhaps the most generic mechanism, the VCG mechanism, correlated equilibria from repeated play, and kind of perhaps, so those two are very classical. So concepts. Bandits with knapsacks is a relatively newer concept. Maybe it's about 12 years old. So I'll cover it in slightly more detail. So there is already, so perhaps the most classic reduction from algorithms to mechanism is, it's not usually phrased this way, but it is a reduction, is the VCG mechanism. It's VCG stands for the authors, Vickrey, Clark's, Groves. There was a Nobel in economics in the 90s, essentially for this work. And it's a very beautiful idea. It's on paper, it kind of solves the problem, at least for mechanism design with money. So what it does is, if you have an algorithm for optimization, it gives you a mechanism with money that on paper looks completely amazing. So it can be, and it also can be summarized in one sentence with like 8 words. So the idea is very simple: maximize total utility, so make everyone as happy as possible in aggregate, and charge each player their externality. Okay, so we'll define it in the next slide, but what the externality is the loss of utility that player I causes on other players. Because so player I exists, their preferences need to be accommodated. That causes some inconvenience to other players, which you can calculate, and the externality is the amount of that inconvenience. So formally, we suppose that there is some outcome space X. So this is the space over which we do the optimization. Let's say each individual Fi has a utility from the space of outcomes to the space of, say, positive reals. So here it's a mechanism with money. So this is denominated in units of money. So when we talk without money, it's actually the first question to ask is what are the units, but here the units are units of money. So the mechanism will output the utility maximizing outcome. So sum maximizing the sum of utilities, and the player, and this is the formula for what player I pays. So this is, as we said, this is the externality. So this would be the hypothetical utility without player I. So if we didn't need to accommodate player I, this would be the best outcome all the other players would choose. And that's the utility of that outcome, minus the realized utility of those other players. So PI is exactly the externality. So the standard example for this is the a simple auction. So where there is one item and n players. And the outcome space is just 1 through n, which acts as discrete in this case. If we don't use lotteries, it just says who gets the item. So player 1 through n. The utility of player I for outcome j is the value vi if they get the item and 0 otherwise. And VCG will maximize utility, so it will give it to the highest value player and charges the second highest value, because if that player didn't exist, the item would go to the second highest bidder. So it charges the loss of utility cost to the second highest bidder. So VCG recovers second price auction in this case. So it's conceptually it's an amazing concept. It has huge advantages. So it's not hard. It's an easy exercise to prove that it's truthful in the strongest possible way. It's dominant strategy truthful. So which means that reporting the true utility FI is the dominant strategy for player I, regardless of what any other player does. So it's just always in your best interest to truthfully report your utility. Always leads to the optimal outcome. The first line is pick the best possible outcome. Completely general. So so far the good news. So game over. On paper, yes, but in practice it has very strong drawbacks, which is the reason why it's actually commonly cannot be used in practice as is. And several reasons for this. So I'll just highlight some of them. There is actually a paper listing, I think 13 reasons from about 15 years ago or some large number of reasons why VCG is so great in theory, but cannot usually be used as is in practice. So, so first of all, it requires money. So some storable unit of utility. So that's not really a drawback because there are plenty of applications with money, but today actually we'll want to talk about mechanisms without money. So requires explicit knowledge of utility. Maybe that's not such a huge drawback. This is actually one of the, so requiring, it's not just that it requires money, it's actually also not budget neutral. It has other issues, but the most important drawback for applying it in kind of heuristic settings is that it completely fails under approximation algorithms, especially if you have many players. So this is because the payment is really a difference between utility with player I and utility without player I. So it's a difference between two large numbers. So, and this is fine if your optimization is exact, but if it's even if it's approximate with a very good approximation factor, this becomes those prices become very noisy and the thing becomes unstable. So if you have 1,000 players, say each one paying $1,000 on average, even if this optimization is within 1%, that would mean that your payment will be $1,000 plus minus 10,000. So if due to some numerical miracle removing you actually makes everyone happier because of the numerical instability, you'll get the mechanism will say to pay you back for essentially nothing. So that's the first type of reduction that we'll use, the VCG reduction from optimization to mechanism with money. The second extremely important reduction is from low regret learning to correlated equilibrium. And so that's in the context of strategic games. So a Nash equilibrium is a distribution of action such that no player benefits from deviating from the prescribed action. And then epsilon Nash means that no player derives non-trivial benefits from deviating. And Nash equilibria are actually pretty difficult conceptually to reason about. For example, even epsilon Nash under reasonable assumptions is computationally hard to find. But in practice, I mean, systems that appear to be in equilibrium, you can reason about the equilibrium without too much trouble. And the reason is that in practice, most of the time, we are dealing with correlated equilibrium. There is some kind of signal that correlates actions. So conceptually, it's very important kind of to understand correlated equilibria. So for example, in a market, prices and other signals from the market serve as a correlating signal. So a correlated equilibrium is the concept is each player observes some additional signal, which without loss of generality could be the proposed actions. And given the signal, each player chooses a strategy. And a correlated equilibrium is a distribution of signals such that when you receive a signal, you don't benefit from not following the proposed action. And epsilon correlated equilibria are defined similarly. So kind of when you teach correlated equilibria in a course, typically the first example of a correlated equilibrium is a traffic light. So you don't, so actually it's an interesting but kind of a little scary game. It's like the game of chicken when there is an intersection without a traffic light and there is a Nash equilibrium that you can compute there. But with a traffic light, when it's green, you know that the other direction gets a red. So it's a dominant strategy to go. And when you see a red, the other party sees a green, and you know that you'll get hit if you don't stop. So it's dominant strategy to stop. And this is the only equilibrium there. Markets with prices is a very generic example of a correlated equilibrium. And it's a very important one because posted prices induce a truthful response from market participants and simplify trade, for example, a lot. So when there is a posted price, so let's say on a market, it elicits a truthful response from market participants. So when you go to the market and there are prices that are already posted, you'll buy your favorite bundle of goods at these prices. So there is no benefit from misrepresenting that. On the other hand, so this is a correlated equilibrium because the prices already have been set. If you have to negotiate the prices, as in a Nash equilibrium, you might try to influence prices by misreporting utilities, and kind of that's what you do when you haggle for prices. So you'll claim, oh, I don't really want this item to drive the price down. And in fact, this is the informal explanation, but there are serious deep theorems like Myerson-Sutter's white node trade theorem that formalizes this intuition that basically there is no, efficient trade cannot happen on in a Nash equilibrium, exactly because sometimes people will pretend, try to lowball their utility to get a better deal. In large markets, actually, there are convergence results that this is not such a big problem, but correlated equilibria are unequivocally nicer in this context. Another important connection between that kind of corresponds to correlated equilibrium is through online learning. So if you kind of never saw game theory, but let's say you were approaching this completely from the algorithmic direction and you were faced with a game, one thing to do is to program some bots that learn how to play. And the bot will presumably run some reinforcement online learning to learn to play this game better in a repeated setting. And roughly speaking, this is a very good idea, and low regret for players corresponds to correlated equilibrium. So if you succeed, which you will, because there are results about online learning that achieve low regret, then a low regret outcome corresponds to a correlated equilibrium. So that's computation. And by the way, this also means that indeed correlated equilibria for explicit games are computationally easy. They also can be solved by a linear program or by an online optimization heuristic. So yeah, formally you need slightly stronger condition, but essentially this is solvable through online learning. So online learning, generally speaking, it's the first time you see it, it seems obviously impossible. The thing that are achieved, like low regret, but generally speaking, anything that's not precluded by an easy information theoretic argument is actually attainable. And often by some version, it can be rephrased. Maybe it's not the first algorithm, but it can be rephrased and as a version of gradient descent. So all the multiplicative weight updates can be rephrased as follow the regularized leader and so on. Some of them more explicitly and others less are forms of gradient descent. So the final ingredient, that we'll need for the discussion is bandits with knapsacks. So the standard bandit or expert setting is the following. There are n arms being pulled over t rounds. You get a reward. Sometimes it's a penalty, but let's say it's a reward. You get a reward that depends both on the arm you pull j and the round t. So reward can change over time. The total reward from actions is the sum of rewards over time. And we have epsilon regret if we do better or almost as well as the best strategy in hindsight. Swap regret is some stronger condition that says that we don't regret playing something else every time. So there is no permutation of, not permutation, there is no renaming of strategies that causes us to do much better. So regret is a special case of swap regret. So with knapsacks, it's a straightforward generalization of this, except in addition to the reward, each item comes with a non-negative cost. So the cost, think about it as you have a knapsack, and at every round you can open one drawer and get the rock from the drawer. So the rock is worth some money, but also it has some weight, and you have to put it in your knapsack. And when your knapsack is full, you're no longer allowed to open any drawers. We assume that you always have the option of not having zero cost, zero reward arm. And now regret is against set of feasible policies. So some policies might not be feasible because you exceed your weight capacity. So, but you want to do as well as possible over some set of feasible policies. So worst case, negligible regret, unfortunately, is unattainable in this model. There is a simple example. So let's say, which is not so. In the standard bandits, you can always attain negligible worst case regret. But here, there are t rounds, and the universe, the budget is t, and the universe selects at random between two possible universes. In one of them, so in both of them, for the first t over 2 rounds, you get reward 1 at the cost of 2. And then for the second t over 2 rounds, you either get nothing or you get a reward of 2 per round. So basically you have to commit to, you're allowed to pull the arm half the time, and you need to decide that you're going to spend your budget in the first half or not. And that's clear that you cannot simultaneously do well in both of those universes. If you pull the arm a constant fraction of time in the first half, then you have a lot of regret in S2. And if you don't, you'll have a lot of regret in S1. So in either case, omega t regret is unavoidable. But actually, the obstacle is a one-parameter obstacle. And all you need to know is the single number to attain same regret properties as in the non-knapsack case, so which is the target bank per buck. So basically, if a little bird whispers to you that, okay, in this universe, you should expect half a reward per unit of cost. In this universe, you should expect 1 reward per unit of cost. Once you know that, you actually can attain negligible regret, because all you do is then replace basically do change of variables and treat it as a standard online learning problem. Okay, so it's been a very long introduction because we had to cover, I hope that you've seen some of those things before, but probably not all of those things. So we had to cover many, and different people have seen different things. So we had to cover many different ideas from different backgrounds. So, but the main ideas are that we have VCG, which seamlessly converts optimization to mechanisms, but needs money and is very sensitive to errors, so cannot be used in a complex algorithm. We have online low regret learning corresponding to correlated equilibria, and we have bandits with knapsacks that up to one parameter correspond to standard bandits. Now let's become even more ambitious. So we are back in the setting where there are utility functions fi. Each player has a utility function fi. We want a mechanism without money. So we'll give them fake money in tokens. And we want we are completely ridiculous in that we want truthfulness and we want a mechanism without money. So suppose we gave them worthless tokens. So each player got B worthless tokens. And imagine that, so they gave us those FIs. Suppose we ran VCG. So we maximize the sum of FIs and charge VCG prices. And suppose a magical miracle happened and the VCG prices came up to B exactly. So everyone's externality was calculated to be B. It's equalized. So since everyone got charged B tokens, it doesn't matter if those tokens are worthless. So then we get a correlated equilibrium. So VCG is truthful, which means that a player cannot improve her outcome while staying within budget B by misreporting her preferences. Right, so even though those are not real tokens, if you say, if you freeze all the players except for you, and we say you're allowed to report whatever Fi prime you like, we will just rerun VCG, and you're allowed to report any Fi you like as long as you don't exceed B tokens. There is nothing better that you can do than to report truthfully. And this is by truthfulness of VCG, even though this is not real money, because all we need is that you cannot simultaneously do better and pay less. So that's so if a miracle like this occurs, we get a correlated equilibrium without money that achieves with the nice properties of VCG of being truthful, at least in the correlated equilibrium sense. Okay, so but this is of course relies on some kind of miracle. Let's try to make it a little less magical. So suppose we gave everyone B tokens. We got the utility functions Fi, and we find parameters lambda I such that when we so those are non-negative parameters such that if we maximize the sum and charge VCG prices, every player still pays B. Then the result again is a correlated equilibrium, and it's again true that no player can improve their outcome while staying within their budget by misreporting Fi to Fi prime. And this already seems less hopeless because the previous slide, we really needed a miracle. Here we can hope to actually find those lambdas or learn them. And this is our main kind of meta algorithm. We call it APEX, adaptive pricing equalizing externalities. So basically, we'll try to learn those lambdas. So we run an iterated optimization loop where at every round, we optimize a weighted sum of utilities. We charge players their externality in tokens. We charge local VCG prices. So if you remember, one of the problems with VCG was that it's extremely unstable numerically. If we stay local, this is not such a problem. So locally, everything kind of can be approximated to the quadratic function, and one way to think about it, where do the lambdas come from? Well, because of the connection to online learning, you could think about it as a central loop where the lambdas are just updated by gradient descent, but it's actually cleaner to think of those lambdas as being learned by the players using bandit with knapsack. So basically, we run we run the algorithm iteratively. At every step, each player is being charged in tokens, and their goal is to they have a long-term budget in tokens, and their goal is to maximize their utility subject to the tokens constraints, which will cause the budget to the externalities to be equalized. Okay, so we are ready to. So this was a bit fast, but we'll go over this a couple more times in the next 10 minutes. So the ingredients is a local heuristic for maximizing functions over the outcome space. So the keyword here is that it's enough for it to be local because the update will be local. And given that heuristic, we assume that the heuristic is some kind of iterative local update that locally looks like a gradient step, perhaps with some regularizer. So what we do is, on top of that heuristic, we intertwine one step of that heuristic with a step of players updating their lambdas and calculating externality costs. And the goal of the players, so basically, at every step there is a local optimization step and a step of computing local prices, local VCG prices in tokens. So that's from the viewpoint of the algorithm. And from the viewpoint of players, at every step they submit a lambda and they get back a cost. They get back an outcome. So higher lambda means my opinion should count for more. And so if I report a higher lambda, I'll be happier with the outcome because VCG will take me more seriously, but I'll also get charged more tokens. And my goal over the long run is to maximize my happiness without blowing through my budget. And this I do by running bandits with knapsacks. So except for this knapsack component, this is a very standard way of looking at a reduction from learning to equilibrium calculation. Here we try to, by adding this local VCG, we try to extend it to an actual mechanism without money. So the main, okay, so it remains open, wide open to see under what conditions this process actually converges. So without, if this knapsack thing wasn't here, this would be game over in the sense that we would have a very generic reduction that basically solves this holy grail question, including in regimes where it's obviously cannot be solved. So it's in some sense for soundness of the field, it's good that we cannot do it. But in a sense, this is enough for two things. So first of all, we get this very encouraging result. If that, so this is a big if, but if the algorithm converges to a solution where each player has low regret, then we get something, a correlated equilibrium from equal endowments, which is generically the strong, I think it's arguably the strongest solution concept you could hope for in this field of mechanisms without money. So it gives you a heuristic that at least it's one-sided in the sense that if you get a solution, you know it's a good solution. The only risk that it might not converge. If you make conditions strong enough, I think there are examples where it's PPAD hard, but in practice, it should work in many cases. So in particular, if you find such an equilibrium, then no player benefits from reporting some other utility function but not their actual utility function. So let's see an example. So it's the simplest possible example. You want to allocate one indivisible item to two players. So the solution space is 1, 2. The utility function of each player is 1 for getting the item, but 0 for not getting. So I should point out that those Fs are in a setting without money, they're already defined in the affine space, because there is no difference between if it's not. So here this one is unit free because there is no money involved. So there is no difference between saying that I value this item 1 or I value it 5, because it's a scaling. Those Fs are only defined up to an affine transformation. So what will happen? We'll give a budget B equals T to each player, and run a repeated. What is VCG in this case? It's a repeated second price auction. And each step, basically, the players bid lambda 1T and lambda 2T. The higher bidder gets the item and pays the second highest bid. And in a good equilibrium, the price will fluctuate around 2. So in half the rounds, one player will win the item, and half the rounds the other player wins the item, and resulting in the outcome, which is in the allocation that gives each player the item with probability half. You can all which is the only kind of reasonable allocation in this case. You can also write an infinitesimal version of this, just to point out that local VCG, it amounts to inverting the Hessian, which is perhaps not surprisingly, but so even though, as we said, that VCG in general can be a very ill-conditioned thing, locally, especially by adding a regularizer, things don't look too bad. So let's briefly discuss applications. So I'll mostly spend most of the time. So the 3 kind of major applications of mechanism without money are voting, allocation, and two-sided matching. I'll spend most time on the one-sided allocation, but let me briefly mention all 3. So with voting, using those ideas, so because the Fs here are cardinal functions, they talk about numbers, you can hope to do cardinal voting. So typically in voting theory, things like errors and possibility results and also positive results, the goals include truthfulness and efficiency, but in some sense efficiency is already being lost if you move from cardinal voting to ordinal voting. So kind of a natural example for this, if you have a setting like this, where basically a third of the voters have a favorite candidates and don't like the other 2 out of B and C, and there is a consensus candidate that voters are happy with. In terms of efficiency, D is the most efficient outcome, but kind of most runoff systems, not all of them, but many of them will result in A, B, or C being elected. So here the outcome space would be distribution space, and you can write take this apex algorithm as a black box, and it actually gives a meaningful outcome. So what you get is some kind of quadratic voting. So each player so basically the equilibrium that you get at the end is somewhere. So this is the space of probability distributions. The outcome is so this is the force field. There could be multiple equilibria, and this is consistent with impossibility results and so on. But in each equilibrium, basically what happens is that every player gets to pick their favorite vote on the ellipse, and this basically they get to pull the vote in the direction of the point that they selected. And the ellipse, there is a regularizer that causes it to get squished near the boundary, which makes sense that if the outcome is 50-50 between A and B and a tiny weight on C, it's much easier to sway the outcome in the A-B direction than to actually change the fraction of vote in the C direction. So this ellipse is usually the Hessian of the regularizer, and the sum of the votes equals to the inverse gradient of the regularizer. So it's promising. Actually, we have nice empirical results, but it's actually in this area we are a bit stuck in terms of how do you argue that this is, what kind of benchmark can we use in order to show that this is actually better than existing solutions, or that it's very competitive with existing solutions. But heuristically, it seems to be very promising. So in the one-sided allocation setting is the one setting where actually there is an interesting theorem that already follows and I should emphasize that I didn't expect this theorem. I kind of expected to reproduce all the results, but it's actually interesting that just plug it into a framework, it gives something new. So the one-sided allocation problem is the following: there are n players and n items, and each player wants exactly one item. So the classical examples is school choice, where you allocate students to schools or students to courses. There is a utility uij for each item, and the outcome space is the space of bistochastic matrices that tells the xij is the probability that player I gets item j. So a classical result of Hyland-Zeckhauser from about 40 years ago says that there is a competitive equilibrium for this problem. You can set prices, you can put a price on each item, create an allocation bistochastic matrix xij such that xi is the player i's favorite bundle if you give them budget 1 at prices pj. So it's very similar to the setting we discussed so far. You create prices, you give each player one token or one unit of tokens, and you tell them buy your favorite bundle of outcomes at those prices. And there is always an equilibrium such that every player gets their favorite bundle at those prices. And those prices are somewhat mysterious, not unique. And in fact, it's proved using fixed point theorem. And in general, it's pretty hard to find such prices. So we get a refinement of this result of the following form. So this is a new theorem. There exists, you can scale the utilities by some lambda i's such that with those scaled utilities, you get prices. The Hyland-Zeckhauser prices are the results of running VCG unit demand auction with those prices, with those utilities. So basically, you can always rescale the players such that if now at those rescalings, and rescaling should be almost thought of as a non-operation, because those utilities in a world without money are only defined up to a scaling factor anyway. So basically we rename them by multiplying by some lambda I, such that with those rescaled utilities, if we run VCG with money, which is just we auction off spots with those utilities, we end up with a solution where every player pays exactly 1 unit of money. So we get Hyland-Zeckhauser prices that are the result of this unit demand auction. So that's another way to think about it. There is an execution of VCG for this unit demand setting, where scaled utilities, with scaled utilities, where each player spends exactly 1 unit of budget, unless they're maximally happy, then they could spend less than 1 unit. And it turns out that it's actually a refinement of Hyland-Zeckhauser, because not all Hyland-Zeckhauser prices are VCG prices for subscaling. Here's an example. So we have 4 players and 4 items. And so this is an example of a Hyland-Zeckhauser location where the prices of A is 1.1, price of B is 0.9, C costs 2, D costs 0, and this is the allocation. So it's supported by those prices. So you can check that every player indeed spends 1 unit of tokens, and each player gets their favorite bundle they can afford at these units. But it's not, those prices are not VCG prices for any scaling, because item B is only, there are only 2 people interested in it. And it's a property of VCG that if you have an item that is not oversubscribed, if there is an item that only that's not oversubscribed, in this case A and B are not oversubscribed, the price of B must be 0 in all allocations. So, and indeed there is a different, there are different prices where B costs 0, which are supported. So there is a VCG outcome, and there is a Highland-Zeckhauser equilibrium that's supported by VCG prices. In this case, B costs 0. So it's a strict refinement. In some sense, perhaps it's a more fair outcome to the first 2 players, because in the previous outcome somehow we charge them to get B even though B is not oversubscribed. And just because we know that they want the B, we make them pay even though there is no justification. And moreover, so this is an almost if and on leaf characterization. So it's not true that all low regret executions lead to a Highland-Zeckhauser equilibrium, but if you add a small regularizer to the mix, which is probably a good idea anyway when you do online optimization, then you do get, then actually every outcome of this algorithm that is low regret gives us a Highland-Zeckhauser equilibrium. So we recover those old theorems in this algorithmic framework. And there is, what goes wrong without regularization is kind of, so here is a weird example. So again, there are so there are 2 players essentially are interested in item A, not interested in item B. So this execution is a low regret execution. So what happens here is, on average, each of the 2 players spends 1 token per round. So the first player wins 2/3 of the time and pays 1/1.5 every time they win. The second player wins only 1/3 of the time and pays 3 units every time they win. And you can see that there is no response that actually improves the outcome for either player. Because the first player is happy to win those rounds, and the second player sees that the first player plays 3 every round, and there is nothing better they can do except for win 1/3 of the time. You need a higher order logic that is not part of this best response logic to say, oh, in rounds where I lose, I'll increase my bid to exhaust the budget of the other player faster. So this is an equilibrium, which implies a stable allocation where the first player wins 2/3 of the time. But with if you add even a small regularizer, this becomes an infeasible solution, because the second player will actually, because of the regularizer term, will be nudged in the direction of making their bids equal over time. So the best response to 3, if you have a regularizer, is 3 plus minus epsilon and not 4 and 1.5. So with a regularizer, this is no longer a low regret solution. So to wrap, a third example that I'll mention only briefly is about 2-sided matching. So again, the vast majority of 2-sided matching work is without money, is in the ordinal settings where you have rankings, and it talks about stability, so the stable matching problem, and its extensions. And efficiency is much less studied, in part because it's very hard to even define efficiency. You can plug it into this framework as is. There is not, it's just another optimization problem over bistochastic matrices. But actually, very quickly, there is a normative, even conceptual difficulty with defining externality, which didn't exist in the one-sided matching problem. And this is really kind of almost, so it's not really a mathematical question, it's more of a conceptual or almost ethical questions. So here is an example of a two-sided matching problem with two hospitals and two doctors. And basically it's clear what's going on. So doctor one is more popular and hospital one is more popular. So there is only one, if you were interested in stability, the only stable outcome would be doctor one, hospital one, doctor two, hospital two. In terms of efficiency, here all the outcomes are equally efficient because the columns are constant. Okay, but that's not what I wanted to focus on. The question is, how do you define externality? So externality in general, remember, it's the inconvenience you cause to the world. So the externality of D1 is the utility without doctor one minus the utility with doctor one. And okay, utility with doctor one, it's clear what it means. It's the utility of all the other players in the actual final outcome. Okay, so the difficulty is, how do you define the without case? Do you include, so when you remove doctor one, do you remove the doctor one completely, or do you only remove their preferences? So, and if you remove them completely, then their externality is actually positive, because the world is better when doctor one is present. If you only remove their preferences, then potentially the externality is negative, because it's always better to have someone, but have them not express opinions about the outcome. So just by definition, your optimization domain increases. So even in this simple case, it's already a little tricky to define externality. In other words, D1 is popular. Does this popularity accrue to her or to the commons, to kind of the global optimization function? If it accrues to her, then the apex actually will output the stable matching where H1 goes to D1 and H2 goes to D2. And if it accrues to the common, then everyone has the same preferences, so the outcome will actually be uniform over the two matchings. So let me just wrap up with some new directions. And so the biggest challenges, I would say, are getting kind of maybe more seeing what this framework actually gives for two-sided matching or for voting. And beyond that, this framework is stated for one-shot mechanisms, but it's unlike some other reductions. This is very easy to extend to an actual online learning or control framework. So here we kind of fixed the preferences once and for all. And this loop that we ran was a completely kind of exercise that was just an exercise to calculate the solution. But you could imagine this loop being actually with evolving FIs over time. It's very easy to integrate into this framework. And moreover, since the main loop actually only does local optimization, we can get by with just the gradient oracle for the FIs. So we don't need the players to tell us what makes them happy. We only need them to be able to tell us what makes them happier from the current solution. So in terms of applications, this is a very important practical problem. So I hope that this turns out to be a lead for kind of a cookbook for converting modern algorithms into mechanisms without making explicit assumptions. What we have going for us in this case is that it's generic. As long as everything is local, it's clear how to kind of apply it to other heuristics. In terms of ML theory, there is an interesting question here, whether there is a statistical interpretation of this idea of equalizing externalities, maybe for robustness. So what does it mean that we decide we have n examples and we want each of those to either have an equal impact or a bounded impact on the final model? And on the optimization side, so it's very cool to think about let's say, calculating correlated equilibria in terms of this. You program low regret bots to play against each other and see what they do, but actually you can rewrite it as a one-shot optimization, basically some linear program. And here an optimization question is whether the main loop can be replaced with a direct optimization. So there are some interesting extensions for mechanism design that but they're in the paper. Maybe I'll skip them because we're almost out of time to leave time for a question or two. Thank you.
Thanks a lot. Thank you very much, Mark. So do we have any questions in the audience? I see clapping. If you have any question, then please feel free to just unmute yourself and ask away. Oh, Edith, yeah, go ahead.
Okay, let me see if my sound works. Can you hear me?
Yeah.
Yeah, Mark, thanks for the great talk. So I was wondering, one classic mechanism design without money setting that you didn't mention is facility location. And of course, it's very well studied, but okay, there's still open problems there. Does your framework have anything to contribute to that setting?
So I must say that I hope so. Actually, it's a great idea to look. I never worked on it before this work, so that's why we haven't tried. But it's a great idea to try, I think. So it is. I guess it is. It's a social. It's almost like social choice, but it's nicer because it has metric structure. So maybe it actually. It can be adapted. Maybe it will commute more nicely, if not in theory, then at least in practice. I definitely thanks. Will definitely. I think it's a good idea to take a look. If you know of work in that direction, I'd be happy to know. If not, maybe we'll try at some point.
Thank you.
Thanks. Do we have any other questions? So one question I have, I mean, it's a very generic question, but here you were talking about the sort of computer science perspective and applications. Do you see kind of when you tell this to a machine learning community, what do they get from it in the sense, you know, in which direction will machine learning take this and push it? Or yeah.
So in terms of, my hope is that it will. So the machine learning community, I mean, one thing that it's very good at is heuristics. Basically, these types of heuristics that are based on local optimization is kind of under the hood of a lot of kind of machine learning practice and advances. Mm-hmm. And what I hope that they'll get out of it is the ability to. So it is important so this mechanism design thinking is very important for many applications, and especially kind of the ones that are being rolled out. And I hope they'll be able to integrate it in the in their models. Even in terms of computation, the overhead shouldn't be too bad. So that's on the application side, and I think this is in terms of kind of applications of computing in general. If you want to use algorithms in the many ways that we kind of are starting to use them now, we need this mechanism design component to be integrated. And I hope that this will be a starting point for another, not the only one, of course, many people are thinking about it, but for integrating kind of mechanism design into the main loop of machine learning optimization. The second one is actually something that I mentioned here, is there is you can treat even so the other thing that happens in most machine learning applications is that there is some kind of empirical loss minimization loop running, which you can think of almost like there are k examples, they want the model to be correct on them, subject to some regularization, and that's what you do. And you could ask what does it mean and whether it's a reasonable question and what settings to equalize externality there. It is a statistics question, and it corresponds to some different way of thinking about regularization. So regularization, one way to think about it is I want to be correct on the examples, but I also have a belief, some kind of prior belief about the world, and I don't like to be surprised. So I'm trying to navigate between those two things. Mm-hmm. And this is perhaps another type of regularization that I don't want any example to get too much weight. Mm-hmm. Whether it makes sense, maybe for robustness, for example, whether it makes sense in practice, I have no idea. So robustness is one natural kind of, if I want one bad example to not be able to sway the model too much, this gives you, I can imagine that the condition equalizing externalities almost gives this to you by default. Mm-hmm. But it's it's speculation, because when talking to ML people, I've been really focused on the first set of problems, even though I think this is also interesting.
Yeah, that sounds very appealing as a like robustness. Yeah, thank you very much for this answer. Do we have any more questions? All right, so then let's thank Mark once again for this very nice talk. And this is the end of the closing lecture, so that's the end of the whole conference. Thank you very much, everyone, for attending, for giving talks, and see you